Okay, let's talk about section 8, Gorsuch's theorem. Um, in many textbooks about analytic functions, they define the analyticity by the differentiability. But in this textbook, we say f is analytic if f is differentiable plus f prime is continuous. Right? So this is a definition in this textbook. And in other textbooks, they only require the differentiability to guarantee the analyticity. So in this section, Gorsuch's theorem, we're going to show actually these two definitions are equivalent. So let's claim the Gorsuch's theorem. It says let G be an open set. And let f from G to C be a differentiable function. Okay, then f is analytic in our sense, in the sense of this textbook, on G. Okay, which means if f is differentiable, then f prime will be automatically continuous. Basically, that's it. All right, so I see the proof in the textbook. We're going to show f prime is continuous. We need to show that f prime is continuous on G, right? And in order to get analyticity. But the continuity is a local condition, right? So we can assume without loss of generality, we assume that G is an open disk. G is an open disk in order to guarantee the continuity of f prime at each single point. All right, so itself, we just, without loss generality, we assume G is an open disk. Okay, so now we will focus on the open disk. And next, we have the Moreira theorem. In the Moreira theorem, it claims, okay, for here, let's recall what is a Moreira theorem. Recall the Moreira theorem. Moreira. This theorem is on page 86. It claims G is a region open and connected. G is a region. F is continuous. And integral f along any triangular path T. The integral f along any triangular path T is always 0. Then f is analytic. F is analytic. Now let's see if we satisfy these properties or not. So here we already assume G is open set, then it is open and connected, so it's a region. F is continuous. This place we need to show f prime continuous, but f is differentiable, it's automatically continuous. And the only missing condition is that the integral of f along any triangular path is equal to 0. Okay, so we need to show that we need to show that integral of f along t is always 0 for each triangular path t in G. Right? So okay, so now let's prove this result. After we prove this condition, then we can claim f is a continuous analytic function. So let T be A, B, C, A. Why we say A, B, C, A? We say this one. Triangular path. Right, so we start from A, move to B, move to C, back to A. So that's a triangle. That's a triangle. Right? Okay, and oh well, it doesn't matter what orientation you put. Here we choose a counterclockwise orientation. You can also choose a clockwise orientation. No difference, because eventually we're going to show the integral is 0. Positive 0, negative 0 are both 0, right? Okay, we have the triangular path. This T only contains those 3 segments. And let delta, capital delta, be the set, the closed set formed by T and its inside. So this delta, this triangle shape, is actually this triangle plus interior part. It's a region, closed region. All right. So when we have T and the delta, we know that T is actually the boundary of a delta. T is a boundary, just really the boundary. Okay, good. And what's next? We're going to divide this big delta into 4 identical delta. How do we do that? We choose a midpoint of each side, and connect them. Choose midpoint of each side and connect them. Okay, so choose midpoints of each side and form 4 triangles. It doesn't matter how you name them. So delta 1, delta 2, delta 3, delta 4. Okay, so possibly let's put here delta 1, delta 2, delta 3, delta 4. The order does not matter. Right? And once we get this orientation, once we have this decomposition, let's check the orientation. So A to B, so because it's already divided, so let's add this. B to C, C back to A. So there's still the counterclockwise orientation. And for the delta 1, we choose the orientation to the right. So you will have the orientation for the the delta 1 orientation is counterclockwise. For delta 2, you see here it's a counterclockwise. Here it's a up left. So this is counterclockwise. So it's still counterclockwise. And here the delta 4, you have a counterclockwise. But the delta 3, we'll see here, it actually becomes clockwise. So go down, up, and to the right. It's clockwise. But anyway, sorry, no. We also need counterclockwise. If we choose this, it becomes clockwise. So we have to choose the opposite way. We have to choose the counterclockwise. We have to choose this way. Okay, we choose counterclockwise orientation for 4 orientation for delta 1, delta 2, delta 3, and delta 4. All right, so counterclockwise. And the reason is that you see here, this segment, you go one up and one down. Actually, if you do the addition about the integral, they canceled. So for all 3 supporting segments, the integration over them will be canceled. And we let Tj be the boundary of delta j. Like T1 is the boundary delta 1, T2 is boundary delta 2, T3 is boundary delta 3, and T4 is boundary delta 4. Okay? Be a triangular path. And then what we have? We have the integral of f along t is equal to sigma j from 1 to 4 integral of f along tj. Right? If you choose the boundary, the big boundary is still the t, but for the interior part, one is to the right, the other one is to the left, one is downward, the other one is upward, one is upward, the other one is downward, so they are cancelled. The integral over the interior 3 segments are actually cancelled. Okay, so by dividing this big triangle into 4 small triangles, we put this compatible orientation. Then you can break this integral into the integral over 4 triangular. Integral over 4 triangular path. Okay, you break a number into the sum of 4 numbers, then definitely one of them will have the maximum ops value or maximum modulus. So among these 4 integrals, there is one. I don't know which one. Let's call it T upper 1, the index, such that the integral of f along T upper 1 has the maximum ops value among those 4 numbers. Right? Always, whenever you have a finite set of numbers, you can always find the number with the maximum modulus. And since we don't know which one it is, so we just put extra index. This T upper 1 could be T1 or could be T2 or could be anyone, right? Okay. From the basic geometry, we know that all 4 triangles actually are identical, are congruent, not identical. They are congruent and they are similar to the original triangle. And we know the perimeter of T upper 1, let's call it, denoted by the length of T upper 1, is half of the length of original interval. This is a half of it. This is half of the bottom side. This is half of the right side. So it's half of the perimeter of the original triangle. And the diameter of T upper 1 denoted by dim T upper 1 is half of the diameter of T. This is equality, not inequality. This is equality. All right. Okay, and integral of f along T should be the ops value of sigma integral f along Tj. And you apply the triangle inequality and replace it by the maximum modulus is less than or equal to 4 times ops value integral along T1, T upper 1 f. You just choose the maximum modulus and control the modulus of the original integral. All right, so here we will get a T1, and then assume T1 is like this, is placed this way. And then we're going to do the same process. We're going to divide T1 into four identical sub triangles, and then go through this process. We'll get T upper 2. So perform the same process on T1. We will get what? We will get a triangle T2, T upper 2, with what? With this property. You see the length of T upper 2 is half of length of T upper 1, which is half square length of T. The diameter of T upper 2 is actually the same thing, half square diameter of T. And the integral f along T is going to be less than this. Okay, first let's copy it here. And then you cover this, and this one is less than or equal to 4 times another 4 integral f along T upper 2. Right? So you will have 4 squared integral f along the triangular path T upper 2. Right? So this is what they called analog properties with analogs properties. That's what the textbook says, analogs properties, this part. Well, you get T upper 2, then you can continue this process. So by induction, whenever you have an infinite process, you will say by induction, we get, or we can get a sequence T upper n of closed triangular paths such that remember T upper 2 is a subset of T upper 1. Okay, such that we have several conditions. Okay, let's see. Condition 1. T upper n is a subset no, it's not a subset. No, it's not. It's not subset. It contains some extra. Okay, let's see. not subset. It's not subset. Delta upper n. Delta upper n is a closed set formed by the T upper n and its inside. Okay, so delta upper n is a subset of delta upper n minus 1. Yeah, this one makes sense. T upper n is not subset. And T upper n is the boundary of delta upper n. Okay. This is a chain, and you have a boundary. Second, you have this one, the integral of f along t minus 1, t to the upper minus 1 less than or equal to 4 times ups value integral f along t upper n. And 3, the length of t upper n is less than or equal to 1/2 the length of t upper n minus 1. And 4, diameter of t upper n is less than or equal to 1/2 the diameter of t upper n minus 1. It's always a half of the previous stuff. Okay, so this is the property for each process. Combine them together. We have what? So 5. First, the integral f along t. You see here you have t upper 1. Where's t upper 1? T upper 1 you have a 4. Here you have a t upper 2, you have 4 squared. Then you have t upper n, you have 4 to power nth power. Integral of f along t upper n. 6, the length of t upper n is less than or equal to equal to 1/2 nth power the length of t. 7, the diameter of t upper n is 1/2 nth power diameter t. Okay, so here is the equality. This one is inequality. Here let's in the textbook they just use L. Simplify it. This one you use D. Okay, the diameter we call it D. Diameter delta is equal to the diameter of T, the same thing for the triangle. Okay, so this one, see here, 1 is contained in the previous one, so the sequence delta n is a sequence of closed sets delta n is contained in the delta n minus 1, and the diameter of delta n, check here, the diameter of delta n converges to 0 as n approaches infinity, right? It's a nest. Not a nest, it's a net. So it's a shrinking. So what we have counter theorem. By Counter's theorem, the intersection of delta upper n and from 1 to infinity is just a singleton. Contains exactly 1 point. It's called Z0 inside G. Remember, G is open disk. All right. Okay, so we do have a point. We're not going to show the function is continuous there. We are going to show that the integral is 0. Be careful. Okay, so a point inside G and f is differentiable. Remember that. So let epsilon greater than 0. F is differentiable at z in G, z0 in G. Then we have, then there is a delta greater than 0 such that this open disk contained in G and what? And the definition of a derivative fz minus fz0 over z minus z0 and minus f prime of z0 is less than epsilon, right? Whenever you have z minus z0 less than delta, you choose arbitrary z from this open disk other than z0. You always satisfy this inequality. Because z minus z0 is not equal to 0, so we multiply this inequality by ops value of z minus z0. So we will have fz minus fz0 minus f prime of z0, z minus z0, less than epsilon times ops value of z minus z0. Just multiply this inequality by this positive number we have. We still have this with the same condition. With the same condition, right? Okay, so you have z0, z0. Z0 you have a triangle, and eventually it becomes smaller. And this delta, this is that radius delta. When this n is sufficiently small, definitely there's, because remember the diameter will shrink to 0, so there is an integer n such that the diameter is strictly less than delta, because remember the diameter is 1/2 to nth power times diameter d. This is constant. When n approaches infinity, this part will approach 0. So eventually, this this number 1/2 to nth power times d will be less than delta. So that's possible, right? And this is the diameter. Z0 is here. It will be diameter is the maximum distance between a pair of points. So Z0 is already here. So any other point will be inside. So this delta upper n will be contained in the Z0, the open disk centered at Z0 with radius delta. Totally. All right. So now let's see the interesting point. We don't know the analyticity of F, but we know 1 Z are analytic in G. Open disk, remember open disk. 1 Z they are analytic in open disk. So by Cauchy theorem, the integral of 1 along T upper n, that's a boundary bit, is equal to the integral of Z along T upper n is equal to 0. The integral of analytic function over this contractible, not contractible, let's not use this word, over this triangular path is equal to 0 in the disk. All right, so this part, we only use the analyticity of those two special functions. All right, so now let's see the integral f along T upper n. It is integral f I'm going to put a lot of 0 here. I'm going to put a lot of 0 here. Okay, so this is 0. It's a constant. Constant function is analytic. Integral is 0. This is a constant function. The z minus z0. It's a analytic function. The integral is 0. F prime of z0 is constant coefficient. So even without the ops value, this is equality. This is equality. So I'm going to put ops value here, ops value here, ops value, ops value. And it's less than or equal to ops value integral t upper n. And this part, oh, sorry, no, let's move this ops value inside. So it's f of z minus f of z0 and minus f prime of z0 times z minus z0 and dz. Correct? So we use a triangle inequality for the integral. And this one, where is it? Here. This works for all the points inside the open disk, bz0 delta. So this t upper n is totally contained in this open disk, so we can apply it. And then here, it's less than or equal to, this is an integral of a positive number, so it's less than or equal to epsilon integral t upper n z minus z0 dz. We're talking about the positive numbers, not the complex integrals. Then we have the comparison. Okay, so this quantity is less than z minus z0. It's less than less than or equal to the diameter of delta upper n. It's the same as diameter of t upper n. The same thing along t, right? So it's a constant. So it's less than or equal to epsilon times the diameter of t upper n. And after you replace it by a constant number, you actually integrate the ops value of dz along the t upper n. It's actually the length of t upper n. Length of t upper n. All right, so first you replace this integrand by this diameter. You change it to be the constant. After you change it to the constant, you integrate the ops value of dz along the path. You will get the length. All right, and this one, remember what we have. We have diameter is 1/2 to nth power d. Length of t upper n is 1/2 nth power l. So it's equal to epsilon dl 1/2 to n. Right, 1/2 to n. Or if you want, you can have epsilon dl 1/4 nth power. Almost done. We are almost done. One step. We're going to use this condition. We're going to use this condition, right? So the integral of f along the original triangular path is less than or equal to 4 to nth power ops value integral f along t upper n. This one. And this one is less than or equal to 4 to n epsilon dl 1/4 to nth power. Well, we cancel 4 to nth power, 1/4 to nth power, so it's epsilon dl. dl is a constant. Epsilon will approach infinity, right? So this will imply integral f along t is 0. Epsilon is arbitrary. So we will get the required condition. This required condition will allow us to apply the Moreira theorem. Okay, it will allow us to apply the Moreira theorem. A Moreira theorem will give us the analyticity of f. So Moreira theorem requires this condition, and the differentiability guarantees this condition. Okay, differentiability guarantee this condition. So if this only you have this condition, then you just need the continuity. If you don't have this condition, you need the differentiability. Differentiability will imply the continuity and plus this condition. So the differentiability is stronger, much stronger. All right, so we finished the section 8, the Gauss's theorem. Differentiability will imply the analyticity directly. So after this proof, we unify the definitions about analyticity. In our textbook, we use the continuously differentiable function as a definition of analyticity in order to get the certain advantage at the beginning. But you can also just define the analytic function directly by differentiable functions. You will have the same class of functions. Okay, excellent. So we'll stop here and continue in the next video. Thank you.